This video is about using list collections in Java. Suppose that we're being asked to write a program that will read all the words from a large text file and store the words into an array list collection. Then once we've finished reading the file, we're going to repeatedly remove the first word from the list, the front element at index 0, until there's nothing left in the list. So this is a little bit of an academic exercise. We're not really doing this to accomplish a larger goal. It's possible that you would use a list in this kind of pattern when you were processing a list of things to deal with, a list of elements to process, a list of people in a waiting line, stuff like that. So the main reason we're going to write this program is to illustrate a weakness of the array list. So I think we'll see that once we've written the code. Let's go to our editor right now. We have a main program here, a client program with a main method, and the first thing we'll do is we'll construct a scanner that reads from the file. In this case, the file that we'll use is the text of Moby Dick, which is a fairly large book file that we've put in the same folder as this program. So this is a really lengthy text file that we're going to read through, count up the words of it. So we've created the scanner for this file, and as you recall from the chapter about file input and output, we can ask the scanner whether it has a next word, and as long as that's true, we'll read a word. And we said that we were going to store these words into an array list, so let's make an array list up here. And as you recall from the array list chapter earlier in the textbook, we will declare that using the type parameter of string, because these words are going to be strings that we'll store in the list. And as we read each word from the file, we'll go ahead and add that to our list at the end of the list. So we'll say words.addWord. And now the exercise that we're trying to solve says that we're supposed to remove the front word repeatedly until the list hasn't got any elements left in it. So what we'll say is, while the list isn't empty, while the words collection isn't empty, we will remove the element 0. So we'll say words.remove 0. And just to illustrate what the program is doing, I'm going to insert a couple of println statements here. I'm going to say system out println reading the file, just so we can see what it's up to. Then here, let's write a println that says removing the words. And here, once that's all finished, we'll have one last println statement that says done. Okay, so let's compile this program and run it. And what we should see is that it takes a little while for the program to finish. Now, the part that's going to take a long time for us to do is this part that removes the words. And in particular, this remove operation is slow. Not just to do it once, but we're doing this remove operation over and over and over until the list is completely empty. So calling remove on index 0 that many times is actually leading to a program that's going to take quite a bit of time to run. I've run it once before starting this recording, so I think it should take about 30 or 40 seconds to finish the overall run of the program. But suffice it to say that this is a really sluggish task for an array list. Array list is not good at repeatedly removing an element from the front of the list. The array list would also not be good for repeatedly adding to the front of the list. Array list is quite efficient when we're dealing with the end of the list. There we go. The program's done running now, but as you can see, that took close to a minute to finish. And you might have noticed that the part where we were reading the file didn't take very long. This part wasn't so bad. We were adding things to the end of the list. So doing things to the very high index, the end of the list, is not so bad, but doing things to the front of the list, index 0, is somewhat slow. So let's talk about why that is and what we can do about it. So if we go back to our slides here, this is a picture of an array list. It's basically got an array on the inside full of all of your elements. This is a list of integers, but it's the same for a list of strings and so on. So we have an array, and these are all the different elements of the different indexes. Now, the reason it's slow to deal with the front of the list is, for example, if I want to remove this 42, the way that the list is going to achieve that is by sliding all the other elements over, like -3 will move over to here, and 17 will move over to here. So all of these elements need to be slid over by 1, And if you have a really large list with a lot of elements, that's going to be quite a number of statements that are necessary to shift all of them over to the left by one. By contrast, if we were going to deal with the far right side of the list, if we were going to put a new element over here and add, the value of 63 here, we just do it. We don't have to shift everyone else over to put a new person there. As long as there's extra space in the array, we can just add that element to the end of the list and there's nothing else to do. So array lists are good for things on the far right when you're changing the list on the far right indexes, but they're not good for the lower indexes. Well, there's another kind of list that we can use if we want to do a lot of manipulations here at the front without a performance penalty, and that's called a linked list. A linked list is also a representation of the same kind of collection. It has the same operations, the same methods as an array list. The only difference is that internally it's actually built with a different structure. Instead of storing its elements into one array, it actually stores each one of them as a small object called a node. And inside of a node, there's not very much information. There's an individual value of the list, a data element value, and there's a reference that refers to another node. And so the way that you implement a list using this kind of structure is by linking together a whole bunch of nodes into a chain. And generally, the overall linked list object maintains some kind of reference to the front or maybe also to the back of the list to access the edges quickly. So the key thing to understand is that you can use both of these objects in a program in Java without worrying very much about how they're implemented on the inside. You don't have to worry about these nodes or manipulating them yourself. You'll just call the same methods on a linked list that you would call on an array list. The only difference is that a linked list is better at certain kinds of tasks than an array list. An array list is also better at certain things than a linked list. So one of the things that's efficient to do with a linked list is to manipulate the edges, the front and the back of the list quickly. So for example, if I decide that I want to remove this 42 here, the way that you do that in a linked list is simply to change the value of this front reference to be a new reference that now points to the -3 node, and now you're done. You actually don't need to shift anybody over because the way that the objects are linked together, you just don't need to adjust those links at all to accomplish this. So that's a very efficient operation to do on a linked list. So if we want that code to go faster, I'll go back to the program here. Remember that it took 40 or 50 seconds for that to finish running. If I go up to the top here and I just say linked list words equals a new linked list of strings, and I compile and I run that, then you'll see that removing the words took almost no time at all. In fact, I'll run it again just to show it again. It's done. Just took a couple of seconds to run that program. So for this particular usage pattern, a linked list is much more efficient than an array list. We're not going to dive into too much detail about how the linked list is implemented. There is a chapter later in the textbook about how to implement a linked list on your own. And so that's where you should refer if you want to learn all the details of the innards of a linked list. But this idea that there would be two different ways to implement list behavior has to do with a concept called an abstract data type, or ADT. An ADT is when you specify a kind of a collection of data and the types of operations that you can perform on the data without necessarily describing the details of how it's implemented and how the data is stored. So in Java, if you want to represent a data type, an abstract data type, you can use interfaces for that. There are some interfaces in the java.util package with names like list and set and map, and those are all things we're going to discuss in this chapter. And those interfaces represent the type of operations that those collections can perform, but each of those interfaces is implemented by two or more collection classes, and those different collection classes might have different structures inside. They might be optimized for certain kinds of operations versus others. So we've just seen that there's two ways to implement a list, as an array list or a linked list. Both of those classes in Java implement this interface named list. So the way that we can take advantage of that in our programs, in our client code, is that whenever we're declaring variables that are going to end up storing lists, so for example, this variable refers to an array list, we generally declare the variable's type to be the interface's type. That makes the variable a little bit more flexible, so it could refer to any kind of list. It could refer to a linked list or an array list. So if I go back to the program here, I could change this to say this is a list of strings named words, and the kind of list I want to use is a linked list to actually implement the structure there. Another place that this comes in is if you have methods. So for example, I might choose to break this code up into methods. I could say something like public static void read file, and I'll pass in the scanner for the input, and I'll pass in the linked list to store the words. And inside there, I'll just take this code and paste it into that method. And now I'll make a call here that says read file. I guess I need to declare the scanner outside in the main. So let's declare the scanner and the words, and let's say I want to use that input scanner and those words. And so that's my way of breaking this program up. You could break up some of the rest of this into methods also, but I'll leave that as an exercise for you. Now, if I declare this the way I had it before, and I compile it, everything should be fine, but then maybe I decide I want to test it with an array list. So I say array list equals a new array list. Excuse me. There we go. If I change it to array list, now the code doesn't compile anymore because the read file method says that it needs to use a linked list, and the main method is using an array list, not a linked list. So a nice way to use these interfaces here is that you can make a method that accepts a parameter whose type is one of these ADT interfaces. That means you can pass any kind of list to this method and it'll handle it just the same because all those classes have the same methods. So we'll go back to our program again, and let's change this file to say that it takes a list of words. And again, let's change this variable declaration to be a list of words. Now the code should compile. I can run it on the array list if I want, or if I want, I can change it to the linked list and recompile it, and the program will still work. The method will allow me to pass either of those kind of lists as a parameter here. So that's useful to use these ADT interfaces when declaring variables and parameters. So the last thing I'll point out is that there are certain things a linked list is not good for. So for example, what if you're writing a method that would delete every other element from the list? So you would delete the 0th element, and then the 2nd, and then the 4th, and so forth. And you're left with, oops, I think I didn't do that right. Sorry, 0th element, then the 2nd, then the 4th is E. So you'd be left with B, D, and F as the remnants of the list after you called this method on it. So that's not too hard. You just write a loop that loops over the list and calls remove with a given index. You'd call remove with 0 and so forth. Well, you would discover if you wrote that code that a linked list would actually perform much slower than an array list. And let's talk about the reason why. The reason is basically that a lot of the operations on a linked list have to traverse the list to get to a certain location. So if you have an array list, you just have a sequence of boxes here. If you want to get to the box at index 4, you can just, Java can do that in almost in no time at all. It can just jump to that index right away because Java knows exactly where in the memory that will be because all of the boxes are stored next to each other in memory. So it's easy for Java to access a given element of an array very quickly. So that means that arrays are good for what we call random access. That's easy to do on an array, and therefore on an array list. If you have a linked list, unfortunately, it's not so simple. If we want to get to index 4 of a linked list, we can sort of assign index values to these nodes here. If we want to get to index 4, which is this one, the 0, the way that the algorithm actually reaches it is that it starts at the front, and then from the front it hops 1, 2, 3, 4 times to reach that node. And the farther that it has to hop, the more time it takes. So unfortunately, some linked list operations are inefficient, particularly ones that deal with, somewhere in the middle of the list, especially when you have a very long list. So if I go back to our problem statement, if I'm going to remove every other element from the list, I'm going to be doing a lot of operations that walk to particular places in the list to delete something. That's going to end up being very slow. So that's unfortunate. The way that we get around that in a linked list is to use something called an iterator. An iterator is an object that lets us walk through the contents of a list without losing track of our position. So for example, you can use an iterator on any kind of collection. Here's an iterator on an array list. The iterator is keeping track of the current position is index 2, and the element at that index is number 9. So you could use it to walk to the remaining elements if you wanted to. You could also use an iterator on a linked list. It would remember that it was at index 3 and it was looking at this element value 2. You could tell it to move on to the next element and it would look at the 0. You could tell it to move on to the next element. Again, it would look at the -1. So it allows you to loop over a list without starting over. If you don't have an iterator and you want to reach the element at index 3, you start at the beginning and you walk to index 3. Then immediately after that, if you want to go to index 4, Java starts the whole algorithm over from index 0 and walks to 4. If you want to go to index 5, it starts over again and walks all the way to index 5. So that takes a lot of time, and it's really silly to have to start that loop all over again. So what the iterator does is it gets you to the place that you are currently, and then if you want to go to the next place, it's just a single hop from there. It's just a single hop from there. So this can really speed up certain kind of algorithms that would use a linked list. So for example, if we were going to write a method to remove every other element from the list, that method might look like this: public static void every other, and this would take a list of strings. And the way that you might write that method would be to say something like, well, let's do a for loop, and we'll remove, and then once we've removed that element, the I++ operation will move us forward to the next one that we should remove. But this will be very slow. So I'll say this is slow for a linked list. So instead, we'll write our code in a slightly different way using one of these iterators. Let me show you how iterators are coded in Java. There's an interface in Java named iterator. In the java.util package, every object that implements that iterator interface has these three methods: hasNext, next, and remove. And so you can ask any collection for its .iterator. That's a method you can call on any collection. And when you call that method, it will return you an iterator that iterates over objects of that element type. And now, once you have this itr object that I've got in my code here, you can call hasNext, next, or remove on that object, and it'll be able to move through the different elements of the collection. And remove is going to be particularly useful for us in this method because we want to get every other element of the list. So the way that we would write this code using our iterator would be to say while, well, we'll get an iterator first. We'll say iterator of strings, itr, equals words.iterator. Now we'll talk to this iter object to access the collection. We'll say while the iter has a next element, we will tell it to remove an element. So we're going to remove every other one. So we should probably read two at a time in this loop. We'll say something like iter.next, and then if the iterator still has a next element, we will call iter.next and iter.remove. So we'll walk 2 steps and remove each time. I guess they're supposed to remove the 0th and 2nd and so forth, so that might be the order that we would do this in. So this is a version of that code that will run much more efficiently than this one. I know that this version that uses the iterator has more lines of code. It might seem more difficult to read, but this one right here is going to take a lot longer to run on a linked list, whereas this one will run much more efficiently on both kinds of lists. This one would be pretty efficient on an array list as well, but this one will be much more efficient on a linked list. That's why we would use the iterator in this case, to keep our code from being too slow.